Hey folks, it's Dave. I'm afraid I have to start this video with a bit of a mea culpa. Um, so the conversation with Tushar went great on the substance, but it turned out that I had set my desktop recorder to record in GDI mode, which led to a very choppy video quality. The audio quality is fine, um, so it may be best to listen to this video rather than watching it. Maybe put it on and treat it like a podcast. Um, but we had a conversation that was almost 2 hours long and turned out really interesting, at least to me. So I hope you enjoy the first episode of Author Meets Physics, even though the video quality is not the best. Future episodes, as you can see from this, will not have the same problem. All right. Hope you enjoy. All right. Tushar, welcome. Hello. Let me start out with just a little introduction to the show since this is the first episode. Um, this is the first episode of a little web series that I'm calling Author Meets Physics. It's inspired kind of by a blog post by Eric Schlieser where he said that it would be great if in philosophy we had more Author Meets Critics events, and in particular, he suggested doing Author Meets Critics events for essays, and I thought that was a great idea. So the idea of the show is that I'll do a kind of, I'll be the critic. I will invite a different author every episode who's written a recent essay in the philosophy of physics that I think is an important contribution to the literature. And I'm Dave Baker from the University of Michigan. My first guest is the first person that I thought of when I had this idea. There was no other choice. My main man, Tushar Menon. We're going to be discussing Tushar's paper, Taking Up Superspace, which is a study of the interpretation of supersymmetry. And Tushar, welcome to the show.
Thanks so much for having me, Dave. It's a real honor to be on the show at all. Doubly so to be the first guest. This is fantastic. I'm really looking forward to it. I think this is just a marvelous thing for you to be doing, particularly for early career people, because you get into that awkward stage where you're not supervised by anyone anymore, and you're not sort of fancy enough to have an author meets critics, symposium at the PSA or whatever. So this is filling, I think, a very definite void that needs to be filled. So thanks a lot, Dave.
Yeah, I'm really looking forward to it, Tushar. And your paper is, it was, like I said, it was an easy choice deciding who to bring on. Your work has had a big influence on me, so I'm excited to discuss it, and hopefully we'll have a lot of cool stuff to go over.
Well, that's very kind of you to say, Dave. Reciprocate is not really strong enough. I think I've said in the past that sort of a lot of what I've written since day one really has been inspired by things that you've written in various different papers, which I'm now beginning to kind of see the kind of guiding narrative thread through, and I'm really enjoying playing with it. So this is great. I'm really looking forward to this.
Well, I hope this. I wonder if this is just retroactive, but we'll see. That's wonderful of you to say that. So, I wanted to start talking about the paper approaches supersymmetry from the lens of the philosophy of space-time, and I wanted to start out kind of contextualizing your views just with application to regular space-time, and we'll get to the supersymmetry in a bit. But one of the cool things about this paper is that in addition to addressing the specific issue of supersymmetry, you lay out a lot of stuff that is really interesting material for the interpretation of space-time theories in general. So even for listeners who aren't interested in supersymmetry, I think we're going to have a lot of stuff at the beginning of the episode to talk about that's going to be of great interest. So along those lines, I want to start with a distinction that you draw between what you call operational space-time and theoretical space-time, right? And part of my MO here is going to be to try to make it clear which parts of the paper I understand and don't understand. So I'm going to try to kind of give my explanation of some of the things you say, and then you can correct or add on to those. But So you draw this distinction between theoretical and operational space-time, and I want to. So the way that you kind of introduce this, I think one of the kind of patterns of argument in the paper, I was saying to you a while ago, reminds me of a pattern of argument that David Albert engages in his well-known paper, Elementary Quantum Metaphysics. So in Elementary Quantum Metaphysics, Albert has this move where he says, we have this, he's talking about space, not space-time. He says we have this concept of space, and we can actually think of it as breaking down into two parts. Both those concepts normally apply, for example, to like space in Newtonian mechanics. But in the case of quantum mechanics, they split apart, and they're actually talking about different parts of the theories. So he draws the distinction between the space of interactive distances, which is, for example, the space along which forces fall off in their effect, things like that. He draws a distinction between that and the space of the stage, he says, on which the world unfolds, which is the space on which the fundamental quantities that everything supervenes take on their values. Mm-hmm. And he says, well, in quantum mechanics, unlike in classical mechanics, the space of interactive distances isn't the same space as the stage on which the world unfolds. So you have kind of a similar move in this paper of saying, well, in previous theories, theoretical space-time and observational space-time were two concepts that went together, and they applied to the same geometric entity. But in supersymmetry, what you call the notion of operational space-time applies to Minkowski space-time, which is kind of a substructure of supersymmetry, whereas theoretical space-time is what's called superspace. Okay, so again, we have kind of two separate concepts of space-time in this case that used to be unified and now have broken apart. So now let me just, and then you can kind of correct me or add on to this, but let me just lay out, as I understand it, your distinction between theoretical and observational, or in operational space-time. So the idea of operational space-time is, this comes from your kind of precursor, Harvey Brown. The idea being that Brown talks about this as chronogeometry, right? The idea that there is this, there's this entity that is surveyed by physical rods and clocks. Whatever the thing is that we measure when we use rods to measure, maybe like proper distances, and clocks to measure proper time. So there's that concept of space-time, and then you say, well, there's a separate concept of space-time, which is theoretical space-time, which you identify with Ehrman's two symmetry principles from World Enough in Space-Time. So Ehrman says in that the symmetries of space-time as a geometric object should be identical with the external dynamical symmetries, right? The symmetries of the laws of nature that govern the evolution of the state through time. So to you, theoretical space-time is that notion of the geometric entity in the universe that shares the symmetries of the dynamics.
That's right.
Okay, so what do you think about this? Do you have anything to add?
Yeah, thanks very much. I think that was a really lovely way of putting it. I didn't mention David Albert explicitly in the paper. I probably should have, because that way of thinking was extremely influential, especially at the time. It was in my sort of early PhD years, and if you're being supervised by David Wallace, then David Albert is a presence constantly anyway. So it's hardly surprising that it made its way through. To refine, as things have gone, as time's progressed, I've sort of thought about how to refine sort of the motivations behind that distinction a little bit more. And I think I hope I have. I mean, it's been a few years since I wrote this. But the basic idea is, I've realized now, captured actually quite well by something that, perhaps unexpectedly, that I got from Sally Haslanger a few years later, where she's also talking about sort of engaging in this process of, in this semantico-metaphysic project of sort of doing a bit of conceptual analysis. And you can ask the question, what is it that we're after when we ask a question like, what is X, right? In Haslanger's case, she's interested in race or gender or some of these social constructs. I'm interested in space-time, but I think similar considerations are at play here. And I think David Albert sort of, does something similar. What I wanted to get across was this idea that you could be interested in a descriptive question, right? What is it that I can say using the word space-time, which is such that if I were to use space-time that way, I wouldn't be laughed out of a physics class, or I wouldn't be laughed at by my friends. Maybe that's a bit strong, because I think they laugh at me quite a bit anyway. But so on the descriptive side, you've got that worry, right? Just the sort of, how do people use this term? But then there's also what Haslanger calls the ameliorative use, which is to say, let's first figure out the point of having a particular concept, and then figure out the best way to flesh out that concept, given the goal that we have, given the role that we hope, that we would like, or that we expect this concept to play. And I think the problem with something like space-time, which is not really a term of art in physics, I mean, it is a term of art in physics, but it's also a natural language term. It comes with a whole lot of baggage. And the thing that I'm interested in is how can we make inferences? What are good inferences that we can make on the basis of particular axioms, of particular theorems, and what are bad inferences? And I think being sensitive to the different ways in which space-time might be playing different roles, not just in different in different solutions to equations or whatever, but also across different theories. I think the way that we use space-time in Newtonian mechanics is quite different in a lot of cases from the way in which we use space-time in quantum field theory. And I think as philosophers, we like the edge cases, right? We spend a lot of time worrying about the edge cases. And I think that the literature slightly reflects this. You'd sort of think that, once you point out that this concept of space-time comes apart from the concept of, I don't know, common external dynamical symmetry group, or that thing that rods and clocks measure, you might think, oh God, we've lost everything. But of course, physicists don't mind, right? Basically, we've got something like 7,000,006 models, of which 7,000,004 are basically fine. And the philosophers sit and worry about the other two. And that's basically what's going on over here. Sorry, that was a long-winded way of saying, yes, I think you've set this up beautifully. And it's really the goal, both in that paper and sort of in the projects going forward, is to try to prize apart the different senses in which you can sort of legitimately use the word space-time, and also then figure out the different inferences that we can make on the basis of sort of pinning down the fact that we mean space-time in this sense, for example, theoretical, as opposed to space-time in this sense, for example, operational.
Yeah, good. I mean, that's helpful, because that kind of got to a thing that I was thinking about asking when you started talking about the ameliorative angle on it, which is, what purpose you had in mind for, and it sounds like the idea is something like splitting up the concept is a useful thing to do, because it kind of creates more logical clarity and less kind of ambiguity about what it is that we're talking about when we say space-time.
Yeah, absolutely. And you can see things like this so another person who's obviously quite influential on my work is Eleanor Knox. And in Eleanor's papers, you can see that there's I think, I mean, she does explicitly say this in, I think, her 2017 physical, I forget what it's called, the one in the Harvey Brown Festschrift, where she basically says, look, the reason we're interested
physical
in
relativity
from a functionalist perspective,
from a space-time functionalist perspective. Yeah, that's right. That's right.
Yeah. Sorry, Eleanor, if you're watching this, I should have all of this at my fingertips.
Yeah, exactly. We should have memorized the exact title of every paper.
And every word. I mean, for what it's worth, I know all the papers. I just forget the titles. But there's a bit in there where she's quite explicit about what the motivation behind her specific kind of project is, which is sort of doing a sort of a functionalist analysis on this concept of space-time. And it's basically a way of saying, look, if I have this concept of space-time and along with it certain concepts of things like space-time symmetries, then it saves me a lot of hard work. It saves, again, this it's not intended to sound like a way of sort of absolving yourself of duties, but it saves you a lot of hard work when it comes to making generic metaphysical claims of the kinds that we'd really like to make, right? You wouldn't want it to be the case that your theory of, supposing you had a view of causation, or some old metaphysical chestnut modality or whatever, that depended on some fact about space-time. Well, you wouldn't want to have to solve Einstein's field equations and solve your dynamical equations and then sort of take your Maxwell fields to the geometrical optical limit to see if they do this in order. I mean, no, that would be ridiculous. That's not good. That's not good conceptual methodology. And one of the things that this concept of space-time does is it allows us to bypass certain getting your hands dirty with certain kinds of calculations while still being able to make good inferences. What I want to say is, you still need to be careful, even when you've established that, for example, what Eleanor says as her characterization of space-time is, in her case, inertial frame functionalism. You still have to be careful about the kinds of inferences that you're not warranted in making, even on that basis. And I should say, you're aware of this, I mean, the paper that you wrote on space-time functionalism was also sort of very much in the air when I was thinking about these things. James Reed and I wrote a paper a couple of years ago where we said, look, even in general relativity, there are possible counterexamples to this claim that if you always have theoretical space-time, then that brings operational space-time with it, right? If you always have this Erman structure, then that automatically tells you how rods and clocks and measuring devices will behave. We had a little counterexample to that in one of our papers, and so this Susie paper can be seen, at least in that respect, as sort of more grist to the mill of the person who wants to argue that these different concepts sort of can and do come apart.
Yeah, great. That's really helpful. So there's a kind of usefulness to separating them. Good. So now I want to start out focusing on one of those two separate concepts, the operational space-time, the notion of the space-time that is measured or surveyed by our physical measuring instruments, rods and clocks, famously in special relativity. So, I wanted to kind of press on the question of how natural of a notion this is, given some kind of like venerable examples. So the examples I have in mind are kind of these things that go back to Poincaré, science and hypothesis. So the question I want to ask is, what does it mean for a rod or a clock to survey a space-time structure, right? So in these examples, Poincaré, thinks of like, well, look, you could have a kind of a finite space that you existed on, where there was kind of a finely tuned physical dilation of all the objects. So like, you might have like a finite circle that you were living on in a kind of flatland type example, but the closer you get to the edge of the circle in these examples, the smaller and smaller your rods get along the direction of the axis of the circle. And so you're never really able to get to the edge. You just kind of dilate further and further. And so the space seems to you, by all the kind of measurements that are available to you as an inhabitant of that space, it acts as if it's an infinite space when it's a finite space. So let's suppose that one accepted an example like that as your theory of the space that you lived in. Then you would say, well, my rods survey this finite space, and they do it in this way that kind of depends on where I'm located. So what you might think is that this kind of example illustrates that there's a kind of theory dependence in the notion of when, to stick with the spatial example, a rod surveys a spatial metric or a spatial distance. We don't know whether a rod surveys a given space until we know the kind of nature of that space in the theoretical space-time sense, right? and I was wondering whether uh, whether you have a kind of first of all, whether that if it's right and there is this theory dependence, whether that's a problem for the notion of operational space time, and whether you have a kind of objection to that line of reasoning if it is a problem.
No, I mean, I don't think it's a problem. I think it's a really good point, and one that needs to be that we need to be clear about. So, I mean, I love the Poincare disk example. The way that I understand, so I'm going to be channeling Harvey Brown over here a little bit, although I assume Harvey reserves the right to disagree with anything that I say over here about this. But I think so. I understand Harvey's response to that to be kind of in the tradition of the Reichenbachian view to an extent, on this similar issue, which is to say that for Reichenbach, Reichenbach's invested in both a semantic project and a metaphysical project, right? Sort of a very deflationary anti-metaphysical project and a very non-trivial semantic project. And his claim is something like, look, if you've got this Poincare disk thing, and you've got, and in a sense, the true geometry is underdetermined by the behavior of the rods themselves. There might be some universal temperature field that, contracts all the rods in a particular way. What he says is, look, the thing that we have epistemic access to is really the combination of a particular geometry and a particular choice of this universal field. And it's, the individual things are underdetermined, but the combination of them is not. And so one way to get around this worry is just to stipulate. Is to just stipulate that when I say 1 meter, I just mean this and such. And then once I've made that stipulation, then to say that something surveys a geometry is really a shorthand for saying it surveys a sum of a geometry and a force field relative to this stipulation of what the universal force field is. And of course, in different circumstances, you might want to stipulate different things. Generally, we go, well, there is no force field, and what's the thing over there? What's the geometry over there? And I think I take that to kind of be the starting point for the sort of the dynamical approach, surveying a geometry kind of worry. Because I mean, the kind of words that Harvey uses in his book, he talks about the operational meaning of the metric, right? I don't think that's an accident. I think the basic idea is, look, the stipulations that we need to get on, we always need some stipulations in order to just get ourselves off the ground, right? Otherwise we're sort of, otherwise it's kind of a slippery slope down the Putnam permutation argument, sort of, in that direction, right? So no, we've got some stipulations. We've solved Putnam's paradox in some particular way. We've made these stipulations, and relative to those stipulations now, the question is, well, in the case of the dynamical versus geometrical approach, which I imagine maybe we'll discuss a little bit later, the question is, having made those stipulations, is there a particular explanatory story about sort of why these rods behave in a particular way, or why the geometry that's surveyed, is the particular geometry that's surveyed? Those are questions to which we now need to bring to bear sort of non a priori, a posteriori even, dynamical considerations.
Yeah, interesting. Okay, there's a lot here, and I actually I think this is probably a pretty good time to begin talking about the dynamical versus geometrical space-time controversy, if to whatever extent you want to bring that in. But let me see. Let me lay out kind of an alternative way that's maybe a little bit more the way I'm tempted to think about this, which I kind of I probably owe partly to Dick Boyd, for example. So here's an alternative. Instead of saying that there's stipulation going on, what about viewing it as a kind of holistic theorizing, in the sense that we have theoretical virtues and norms that make some hypotheses more plausible than others about, in this case, really what we're talking about in essence is what Boyd, among many others, kind of refers to as the background assumptions or background theory that goes into our understanding of our measuring instruments, right?
Mhm.
And so, you know, again, the lesson I've kind of taken from his approach is, well, maybe the thing to do is to um, draw some inferences about what our measuring instruments are probably like on the basis of theoretical virtues, as well as kind of um, maybe a kind of reflective equilibrium between
Mhm.
those theoretical reasons and the empirical data that we collect. And then, you know, uh, instead of viewing this as a convention, view this as something we genuinely believe to be true about, you know, um, so if I were living in a Poincare disk, I would have a genuine belief about whether it was a Poincare disk or an infinite space. And that would inform my theory of my measuring instruments. And that theory of my measuring instruments would tell me what structure is surveyed by them in your sense, right? That's kind of like, does that feel, I mean, is that, to what extent do you see that as something that has to be an opposing view for one thing? And
Yeah, that's exactly what I was thinking. So I'm not. It's not clear to me that that is in any sort of significant sense in opposition to the kinds of things that I was thinking, because it's. I mean, it's not enough just to say, oh, it's conventional, and then twiddle your thumbs and move on, right? The point is that there are some conventions that are more useful than others, and the second the second you bring in utility, right, you're then thinking, well, is it useful? You know, you might start asking some kind of explanatory questions about sort of what it is that grounds the utility of particular conventional choices, right? So I think the sort of the Boyd way of thinking is sort of maybe a little bit further along the spectrum that I'm willing to go,
I
but
see.
it's certainly not in opposition to anything that I'd want to say.
Okay, so it's like that's your view plus the further inference that because it works so well, it's probably true.
Yes, yeah,
Yeah,
precisely.
okay, I see. Yeah, and then now, do you are you more partial then towards a kind of uh, like agnostic picture of the metaphysics underlying what's going on here, or is it? I mean, I guess because there's ways of being non-committal. One of them is to be agnostic, and the other one is to be um, kind of like uh, semantically indeterminate, or like, oh, that's a meaningless distinction or something. I'm wondering where you fall along
Yeah, so that's a good question. It sort of depends on what day of the week it is, because I do sort of go back and forth quite a bit. I mean, in the context of sort of a slightly distinct debate over metaphysical inferences from symmetry considerations, which I'm sure we'll get to eventually. I feel like there's a similar thing going on there, where you sort of kind of good philosophical hygiene mandates that you be agnostic, but you can still feel like you're justified in making certain posits, even if you don't have any sort of even if you don't have any evidence for quote unquote evidence for those posits, right? You might subscribe to some kind of broadly deontological view of justification, where if you don't have any obligations not to believe P, then you're perfectly justified in believing P.
here.
And I think that on alternate days of the week, I think I'm sympathetic to that view of justification.
Yeah, I never realized you were von Frossenite. I mean,
Well,
in this kind of limited. Uh,
yeah.
yeah, yeah. And now, um, did you want to talk a bit about the dynamical view to contextualize your approach in that tradition, which I know you
Yeah,
belong to?
yeah. Yeah, I mean, I think so. There are a couple of things. So one thing that I want to definitely make clear is nothing that I say in the paper or generally want to argue for relies on the dynamical approach being the correct way to think about space-time geometry. But we're all products of our environment, and this is the language through which a lot of this stuff is just the most clear to me.
It's
And
funny, by the
so,
way, when I was in grad school, the stereotype used to be that the language through which Oxford PhDs thought about everything was the many worlds interpretation, but it is since
yeah,
now it's
yeah,
that the language that they all think about everything through is physical relativity.
Yeah, because I mean, by the time I got to grad school in Oxford, the Everett wars had sort of played out more or less, and the oddly, I mean, physical relativity came out in 2005, and Harvey's been talking about this for many years before that, but it's sort of, I don't know, it's sometimes these things take a little while to sort of hit a critical mass, and then suddenly everyone's talking about. So there were two things that were kind of that were very much in the air amongst the philosophy of physics grad students when I was doing my DPhil. One was dynamical versus geometrical, and the other was the kind of work that Neil Dewar and Tom Muller-Nielsen were engaged with respect to interpretations of symmetries and sort of sophistication reduction stuff. And of course, supersymmetry is this lovely area in which sort of all of these discussions can happen. I should point out that at the risk of making this sound a little bit culty, because I know you and I are sort of dyed in the wool cult members. Supersymmetry is great. Philosophers should look at supersymmetry because hopefully it'll become clear that a lot of the questions that we're interested in are approachable and also sort of discussable through a different lens using supersymmetry. And the math isn't actually is not anything that we're not kind of already used to. It's just sort of smushing together things that we might have thought were disparate, and then looking at the metaphysical consequences. Anyway, sorry, that was a bit of a
you're exactly right.
Thank God you can edit this, huh? But I mean, knowing my every time I say thank God you can edit this, it always ends up in the final video online, and I'm sure this will be no different.
Yeah, we'll see. Yeah.
But yeah, to come back to the dynamical geometrical stuff. So the basic idea is something like, again, it comes back to what sorts of inferences do you think you're licensed to make on the basis of particular claims that sound uncontroversial, right? So take something like quantum mechanics, right? Think of things to do with no signaling, or things to do with action at a distance, right? The worries that people have about those sorts of things. The second you write down, a model where you say, look, I've got a Minkowski metric, that brings with it certain claims about no matter which kinds of fields we're talking about, there are certain things that just can't happen. There are certain dynamical evolutions that are just precluded by the fact that we've said space-time. We've included the word space-time in our description of what's going on over there. And the dynamical approach basically asks, I mean, the dynamical approach is sort of totally happy with that. And then it asks the question, well, in virtue of what is this an inference that we're allowed to make in certain contexts? And I think a way to think about sort of where the disagreement lies is just think about the kinds of things that we say when we say, look, these are the dynamical symmetries of all of our fields, right? Take things in the actual world, right? We've got the electroweak force, we've got the strong force, we've got a whole bunch of things. They've all got a bunch of different symmetry groups, right? SU3, SU2, U1, whatever. But they're also all invariant under Poincare transformations, right? There's a common external, I won't say external at this point. There's a common symmetry group, and so you might say, okay, well, does the fact that there's such and such a common symmetry group allow us to explain certain facts about dynamical evolutions? The answer is absolutely. And so then you say, well, in virtue of what is the dynamical symmetry group this thing? The Poincare group or whatever. And that's where the debate begins. Because for the proponent of the dynamical approach, it's just a brute fact about the actual world, right? Some contingent fact, we happen to live in a world like this. For the proponent of the geometric approach, it's something about the fact that there is this entity in the actual world. Let's imagine a special relativistic world for now. So there's a Minkowski metric, and in virtue of the existence of that metric, the symmetry groups are constrained to have this property. And you can then ask the question, well, what happens if I add an extra field in there, right? I imagine a possible world that's exactly like this one, but we've added some extra field. Will that extra field be Poincare invariant, among other things? And I think the proponent of the geometrical approach will want to say yes, because that's what the presence of this geometry does. And the proponent of the dynamical approach will say, well, I don't know. In some nomically possible worlds, maybe in others, maybe not. And I think to bring this back to these things about supersymmetry, I think this is a semantic claim that I think Harvey doesn't want to make, but I think a natural semantic claim to want to make is it's perfectly fine to refer to that Poincare symmetry group as a space-time symmetry group, as long as everything abides by its directives. The geometrician wants to say, well, in some nearby possible world where I've added another field, I can continue to refer to that Minkowski metric as space-time. And the proponent of the dynamical approach wants to say, well, no, I'll now need further information about how fields are behaving in that particular world before I allow myself to use the word space-time.
Yeah.
Once I've made that observation and I see that everything's as it was in that other nearby possible world, then I'm perfectly happy to use the word space-time. And that's kind of what sits at the heart of the, or at least one of the arguments for the manner in which we might be able to think of superspace, which is a particular kind of formalism in which you can express supersymmetric theories, as being spatiotemporal.
That's a good way to put the distinction. I like this thought experiment about, what if we were to add it. So let me kind of so I'm more of a geometrical person as you kind of draw the distinction, and I thought of an analogy as you were talking, which I feel like works as a kind of maybe a bit of a motivation for a view more like mine and less like yours. So I wonder what you think about it. It just occurred to me just now. So think of, like, for example, sources in field theories like electromagnetism. So suppose that I have a distribution of charges and some fields in electrodynamics, and I'm thinking, and the laws, Maxwell equations and the Lorentz force law tell me how those two types of entity are going to interact, right? I can ask a question that's parallel to the one that you were just suggesting, which is, suppose I introduce like some new excitations into the electromagnetic field in this solution, right? Like I add some plane waves or something like that. Are the charges still going to behave like the sources? That is to say, would the new solution be compatible still with those same laws according to which the charges are sources for the field? And a natural thing to say is, yeah. The right way to answer that counterfactual is, this is spinning off in some ways from Mark Lang's view of laws, which I like, but it's not, doesn't presuppose this. But yeah, you would say if I had a different arrangement of fields, Maxwell equations and Lorentz force law would still be obeyed, and so the charges would still act like the sources for the fields. On the other hand, one could take the opposite view and say, no, like if I introduce a new plane wave into the theory, I could just introduce a new wave that would break those laws, and then the charges would no longer act like sources. To which I think the natural response is, but that would be physically impossible, and yeah, like I could imagine doing that, but it would require breaking the laws in a way where now I'm effectively considering a metaphysician's thought experiment instead of a physical thought experiment, right? And so then the geometrical person, the geometrical thinker about space-time would say something similar, that if you are imagining a situation where a new field breaks the symmetries of the background space-time, you're imagining a metaphysical possibility, but something that breaks one of the very central physical laws in a way that makes it kind of like extremely physically impossible.
Yeah, no, that's really good. I wholly agree with this setup. I think you're completely right. There's just one thing that I would add to that, which is I think the way that one way that the I'll go back to dynamical versus geometrical rather than the electromagnetism example. But I think one way to think about what the geometrician will say is here, is this new situation will be a nomically possible world according to the laws in the act or whatever in the reference world, right? The proponent of the dynamical approach will say it could be one or the other. It could continue to be nomically, it could continue to be a nomically possible world according to the laws of this world, or it might cease to be nomically possible and be merely metaphysically possible. And I think the geometrician only has one option, because the geometrician doesn't want to say there's a metaphysically possible world that's not nomically possible, in which this is the case, as I understand it.
I think different geometric approach people would break down differently on this, because to me it seems, like I think of metaphysical possibility as a very capacious notion of possibility, and it's like I feel like if I think there are metaphysical possibilities where the events of the Lord of the Rings play out, I also think it's pretty likely there are metaphysical possibilities where you have a field that doesn't conform to doesn't conform to space-time. But I mean, that said, there's kind of semantic issues there. Would it still be space-time per se in that universe?
Yeah.
So it's we get into the question of space-time functionalism here. I think one can adopt a version of the geometric view and be a sort of space-time functionalist.
Oh, certainly. I completely agree with that. I've long maintained that. I mean, again, it's one of those things where Eleanor is coming from sort of a similar background to me, and sort of that's a sort of dominant view in sort of South England in the early 2000s. But I think a lot of people mistakenly think of space-time functionalism as just something to do with the dynamical approach, sort of maybe spelling out the dynamical. I think it's totally separate. It's wholly its own thing. And yeah, I'm sorry. I was just to briefly come back to the metaphysical versus nomic possibility thing. I think there's a resonance with some of the kind of relationalist, substantivalist, Newton's bucket type worries, where I think similar things are at issue, right? The claim is something like, take the globes, take the Newton's globes attached with a string. And the idea that for the relationalist, it's not possible for the intersphere distances to remain the same and the tension to differ unless these are all nomically, unless they're all possible worlds with different laws. And there's no set of nomically possible worlds in which the distances remain the same, but the tensions are all different. Whereas for the substantivalist, that's not the case. And I think there's a similar kind of dialectic going on there, where the relationalist just wants to say, look, I don't want to be held to your standards of what counts as nomically possible. This is my own standards of what counts as nomically possible, and by my perfectly acceptable standards of nomic possibility, the relational story is perfectly fine. I don't mind conceding that the tension of 5 newtons and the tension of 8 newtons are different, correspond to different physical laws. And I think something similar is happening with the dynamical geometrical case. The complication comes in because there's also a further question of, well, okay, granting these two different views about how we should carve up the space of metaphysical possibility. Now there's a semantic question of what in each of these worlds am I allowed to refer to as space-time. And I think that's when you bring in all of these other sorts of considerations, like common external dynamical symmetry group, or space-time functionalism, or a thing with 8 letters. I don't know, whatever you want, right? So
yeah, interesting. Great. Okay. Well, I think this is plenty of kind of background on this anyway to get us where we need to be to talk about what you have to say about supersymmetry. Now, and one of the things that kind of came out in what you were just saying actually was something in the paper that we have disagreed about in previous work, which is um, this idea of defining the external symmetries as the kind of common symmetry group of all the fields, right? So this is one of the things that you kind of like. I think this is kind of like one of your contributions to the dynamical approach is kind of saying like, this is the way to break down the space-time component of the total symmetries of our theories. It's, as you say, the common symmetry group of all of them, right? So, to kind of lay out the view a bit more, as I understand it, think about the standard model, right? We have, three different forces with three different symmetry groups, strong, weak, and electromagnetic force, each with its own kind of internal symmetry group. And then in the regular standard model, in ordinary special relativistic quantum field theory, there's this other symmetry group that all the fields share, which is the Poincare symmetry, what's ordinarily thought of as the space-time symmetry. And your thought is, well, what makes it the external symmetry is the fact that all the fields share it in common, right? And that works great in the case of the standard model. I do have the concern, which again, like you're totally in the paper, you're totally upfront about this, that, in a theory like just kind of quantum electrodynamics by itself, for example, the parameter space of that theory has two symmetries. It's got two fields, the Maxwell field and the Dirac field, which is the electron. And those have a common Poincare symmetry. They also have a common gauge symmetry that kind of transforms them both together. And so, both the symmetries of the theory are common symmetries that the theories have. And so, like, there's kind of this uncomfortable position. Do we think of the Poincare symmetry as the total theory symmetry? Do we think of the gauge symmetry as the total theory symmetry? Do we think of the combination of the two of them, like the Poincare symmetry cross with the gauge symmetry as being the symmetry of the total field, right? It's well, yeah. What do you think about that kind of example?
Yeah, no, I mean, it certainly is I think I called it a counterintuitive sort of consequence. I mean, it's much more than, I mean, sort of possible worlds with one or two fields are where my intuitions go to die. So, counterintuitive is not really, it's not a bad word in those scenarios, I think. So I've been thinking about this a little bit, sort of on and off since you, because this is one of the first things you said to me when we spoke about this early on when we spoke about this, and my thought about this is something like, look, what is the intuition that we're the sort of cognitive intuition that we're trying to that we capture by talking about something as being a space-time symmetry, and the idea is something like, look, what are the kind of paradigm space-time symmetries? It's things like translations or rotations or whatever, boosts, and really what sort of, at least from my perspective, what's going on there is when we're really thinking about how would things look different? What is the change of perspective that would result, and how would the physics look from the perspective of someone kind of like me, complex, human being, blah blah blah. And I think what grounds the intuitions that we have about those sorts of transformations in really complex worlds like ours is the idea that, look, all of whatever it is that governs the dynamics of the stuff that eventually leads to my cognitive processes in such a way that I can have an intuition about what things would look like if I rotated and looked at this microphone from there. Those are just not at play in these much simpler worlds, right? In these much simpler worlds, the thing that's contrary to our intuition is the idea that, oh, I could sort of rotate in the U1-y kind of space, or I can rotate in the kind of Poincare-ish sort of space, or somewhere in between. But I don't think you can set up that counterfactual sort of sufficiently robustly in order that it clashes with my intuitions, as opposed to just making it seem like I have no intuitions about what's going on over there. And so I have no problems admitting that in cases like that, yeah, for the kinds of again, this comes back to what is the purpose that we're putting this word to. For the kinds of purposes that we put the word space-time to, for example, things to do with what a rod or clock might measure, or things to do with causality, or whatever, or for example, something that we might talk about a bit later, the kinds of things that Michael Redhead and Robert Weingart have said about ontological unification, which is also something that you discuss in your Susie paper. For all of those things, I think these sorts of single field or two field worlds are sufficiently impoverished that I don't mind that you get this kind of counterintuitive result that sort of everything or nothing counts as space-time. That's my sort of that's my get out clause.
Yeah, it's interesting. I mean, so one thing that I guess kind of when I try to think of what would make the kind of thing you're saying here more plausible to me, I think maybe, yeah, like some people, Frank Arnzenius, for example, have thought that maybe we should interpret the fiber bundle as being the basic, like, space in which everything exists or something, and be substantivalist about that. So that might be a kind of, it's like be a kind of, think of the fiber bundle as like the spatiotemporal structure or something like that. That kind of fits.
Yeah, I mean, I'm quite sympathetic to that sort of thing. Maybe not all the way. Maybe not going all the way along the frank substantivalist view, but certainly. So there's a paper that Jim Weatherall wrote a few years ago about interpret sort of Yang-Mills and gauge theories and fiber bundles, and he wanted to tell this this deflationary story, right? He wanted to say, look, I don't care about the principal bundle. Think of how we do. Think of how we do general relativity. We never have to mention the principal bundle. We do it all using tangent spaces. We can say a similar thing about Yang-Mills fields. And it seems like what you're suggesting is kind of pushing back against that and saying something like, no, look, let's take the principal bundle seriously. The question about whether we should think of that as sort of spatiotemporal. I mean, I don't think Frank thinks of it as spatiotemporal, right? He just thinks of it as sort of a fundamental space, sort of a real space. It's not fiber bundle space-time substantivalism, right? But it's, and I think
that's right. Yeah, I didn't mean to say that this was all there.
I know, but I think so. I think in that case, to get off the ground. So if I wanted to make the claim that there was a specific, that one of those symmetries was going to be the space-time symmetry group and the other one was not, then I'd need to be committed not only to some kind of fiber bundle, let's just call it fiber bundle primitivism, maybe, or fiber bundle realism, fundamentalism, I don't know. But on top of that, to some kind of almost stipulative claim that, transformations on the base space correspond to space-time transformations, or transformations of a particular type sort of correspond to space-time transformations. As it happens, actually, there might well be particular idiosyncratic uses of the word space-time, such that particular inferences would actually go through on that particular use of space-time. I mean, I can't think of anything off the top of my head, but I don't want to rule that out. But I don't think that my identification of sort of the common dynamical symmetry groups for when there are two or more fields. I think basically what that means is I'm pretty neutral on what happens in the one field case.
Mm-hmm. Yeah, interesting. Yeah, I mean, it's if I had to say what seems a little odd to me still about the picture, it's that our spatial and temporal concepts, like as they fit into mathematical physics, kind of originated in a theory that was like a one field theory, like in Newtonian gravity. Mm-hmm. So it's like I guess that makes me feel like my intuitions about space and time are at home in one field theories rather than being, it's like it's only relatively recently that we've had multiple field theories that have been like formulated with any degree of
Hmm.
completion, and I mean, still they're not formulated with with complete rigor by any means. You
Yeah.
know, for thinking of the standard model, but yeah, I guess
No,
like
that's a really good point. So presumably I mean, think of something like a corollary six symmetry, um, where yeah, you've got a gravitational potential, you've got space-timey structure, and it kind of yeah. No, I think you're right. I don't. I wish I had a knockdown argument, but I guess I mean what I could say in that case is, luckily I don't commit to anything in the one field case. So
yeah,
so
okay,
that so I so I'm sort of open to the idea that that there's something else then that picks out. Again, there might be
ah,
something else that picks out spatiotemporal, something that's sort of unequivocally spatiotemporal in the appropriate sense, in the sense that
okay,
sort of continue that sort of has is sufficiently analogous to the way we use the word space-time in Newtonian gravitation theory
so
to
so so
to work.
the idea maybe is that the common symmetry group of multiple fields, being the common symmetry group of multiple fields, is sufficient for being a space-time symmetry, but it's not necessarily necessary, and there might be other sufficient
Yeah,
conditions that
yeah.
apply in the single
And,
field
and and
case.
further, I would think what I want to say is being the common symmetry group is sufficient for being a theoretical space-time,
Yeah,
for
yeah,
giving rise to a theoretical space-time. And then the next question is, okay, well, you've given me this theoretical space-time. What the hell am I supposed to do with it? And the answer is, well, what are the kinds of things that you usually do with theoretical space-times in things like um, special relativity? Well, you infer certain facts about you might infer certain counterfactual facts. What happens if I were to add another field? You might infer certain facts about the behavior of light rays or whatever. And then the sort of what I want to say is, well, okay, now let's take it out of the sort of nice sort of hometown feel of special relativity and move into something like supersymmetry. Which of those sorts of inferences carries through? And I mean, I don't attempt in this paper, and I don't think I really could give a sort of exhaustive characterization of how each of these different kinds of space-time is useful. I think this is the point is more a sort of cautionary look, go ahead and do it. But then if your inferences break, if you get a whole bunch of sort of weird stuff coming out, you kind of know here's one place where you can look for where your inference machine broke.
yeah.
I think that's really what I wanted to get across.
Okay, that's good. That I mean, that's great. This has advanced my understanding of your thinking. Actually, this is good. I now I have a better sense of what you're getting at. Wonderful. So let's talk about supersymmetry then.
Cool. Yeah.
Susie, as they say.
As
Um,
all the cool kids say.
yeah, exactly. So the idea here is that you have an additional symmetry. So you take a theory, um, take a theory that's a composite theory that has a boson field and a fermion field in it, um, and you uh, you tune things so that the two have the same mass, and then you've kind of you introduce a new symmetry, which is um, uh, you know implemented by these operators, the Q's, the supercharge operators. Excuse me, and these you know uh, uh, remove a fermion and introduce a boson, or vice versa. And the thing that we notice about this, which is super surprising, is that
Super surprising.
yeah, super surprising. Everything's gonna be super from now on. So the highly surprising thing that we learn is that when we introduce these operators, they also perform space-time translations um, in addition to interpolating between the Bose and the Fermi field. And so that looks very suggestive, and indeed we can define this larger symmetry group, the super Poincare group, of which the regular Poincare space-time symmetry group is a subgroup. Um, which acts on this other entity we can define, at least in some supersymmetric theories. Not all of them have a version of this that we know of yet. This entity, superspace, which has extra dimensions that are naturally coordinatized by anti-commuting Grassmann numbers. And, the metric is, a metric on which these, the kind of like analog of distance along these extra dimensions is parametrized by Grassmann numbers. So like, I mean, I guess the thing that I sometimes say to people when describing this is that if you fix a convention that a certain origin along those Grassmann directions is where the boson field, the pure boson field exists, then kind of like the further you get down those dimensions, the more fermionic the system is or something. Like, it's like I always hesitate to say that that's a completely accurate way of describing it, but it's but it is true that you can conventionally set an origin and say that's the purely bosonic part of and then you define you can define this extra this further entity, the superfield, which is kind of a composite of the Fermi in the boson field, and then what these supersymmetry operators do is they translate that superfield in superspace, right? So then the question on our plate here is, you have these two separate concepts of space-time, operational and theoretical. Does that superspace meet either or both of these definitions, right?
Yeah.
So I think that kind of so the part of your view that we've kind of engaged the most on and that I think I get the most is your argument to the conclusion that superspace is theoretical space-time, right? And I mean, it's not, when I say I get it, it's not very hard for me to get because it's kind of like, it follows pretty straightforwardly from the definition of theoretical spacetime that you're using, right? So if the definition of theoretical spacetime is the common symmetry group of all the fields, then, well, Poincare symmetry is no longer the common symmetry group of all the fields. It's, it's the symmetry group of the component fermion and boson fields. Supersymmetry is the symmetry of the fields taken together as the superfields. And so the argument goes, that is theoretical space-time, right? Have I represented it?
Yeah, no, that's spot on.
Yeah, good. Okay. So let me kind of then so one thing we could do is bring back the dialogue we had before about the geometrical versus the dynamical views of regular space-time. We might ask, if you were to introduce new fields into this, for example, would they be superfields or would they be potentially just boson or fermion fields by themselves?
Yeah.
Right. Now, I guess you would say, tell me if this is right, you would say that the view that a new field might be a superfield or it might be a boson field or it might be just a fermion field is compatible with the thesis that superspace is theoretical spacetime, because as a dynamical theorist, you don't consider that to, okay, interesting. This is an angle on this that I hadn't actually thought of before. Yeah, cool. Okay. So Um,
Although I should say, sorry, Dave, just on
yeah.
maybe that was a bit quick, right? Because so presumably the idea is we've got this super space, we've got a super field on a super space, and now I've you know God has given me another field that I'm allowed to chuck into that world to make a new world, and now I say, okay, is it the case that if I chuck a bosonic field in there, that it'll automatically sort of be a component of a superfield? Can I chuck a bosonic field out there into that world without it bringing along with it a fermionic superpartner field in a way that and okay, so I want to take back my agreement sort of a little bit. I want to sort of dial back on that a little bit. What I'd want to say is the dynamical approach will be consistent with either of those scenarios, right? Either just a pure, but the semantic claim that I think is most natural on the dynamical view, which is that superspace is space-time, I think that's going to be broken, because the second that's going to be broken in one of those cases, right? That'll be broken in the case where the additional field is not supersymmetric.
Yeah.
Because now you've got, because then in that case the space-time symmetry, I don't want to say the space-time symmetry will be broken, because that has a very specific technical meaning. But in that case, it would be appropriate to use the word space-time only for the Minkowski component rather than the full thing.
Yeah. Good. That seems exactly right. So and I think that that's true of the examples we were discussing before as well, right?
Yeah.
So the dynamical theorist who wants to talk about space-time, which Brown doesn't really, I guess.
Yeah, no.
Yeah, but the dynamical theorist like yourself who does want to talk about space-time would say, oh, there's no law that says that a new field can't have different symmetries from the space-time symmetries of the other fields. But then if that happened, you would have a new definition of space-time, and it wouldn't be the same as the one that you had before.
Yeah.
And
in particular, a new definition of theoretical space-time. Yeah.
Yes, exactly. Yeah, you'd have a new definition of good. Good. Yeah, that makes perfect sense. And yeah, that's kind of, in a way, that's kind of like the space-time functionalist component of what you're saying. So what you're saying has kind of two parts, like the dynamical theorist component, which is, yeah, like, if you introduce new stuff into the world, it might or it might not obey the space-time symmetries of the theory that it has to start out with.
Yeah.
Neither of those possibilities is kind of more prohibited than the other. But if you, the space-time functionalist part is, if you did introduce new stuff that didn't obey the space-time symmetries that were there before, well, then what you were thinking of as theoretical space-time no longer is theoretical space-time.
Yeah, absolutely. Yeah. And I should say this is space-time functionalism sort of on the more in the Baker vein than in the Knox vein, right? Because Eleanor has sort of a very specific kind of functionalist, whereas I think the Baker view is sort of specify a function and then sort of see how it plugs into this list that we have, et cetera, et cetera. So it's functionalist in that sense.
Yeah, the flexible sense.
The flexible sense.
Yeah. Whereas Knox has a more regimented notion of space-time function. We should talk about Knox, which you do very much in the paper. So Knox's definition of space-time is whatever plays the inertial role, right? The role of deciding which frames are the inertial frames. And so you have an argument that superspace is like that in supersymmetry theory because it is the structure that gives us super inertial frames, right? So there's an analog of inertial frames you can define. Yeah. Okay, cool. Did you want to say more about that argument?
Yeah. So I think again, this plugs into the sort of the broader picture. I think I was just thinking about this. I think one way of thinking about how sort of the use to which I'm putting these different versions of space-time is something like the following. We can one way to characterize a theory is obviously, just the standard way, right? A bunch of equations, dynamics does this, symmetries do that, blah, blah, blah. But supposing we're not interested in those sorts of idiosyncrasies, we're interested in sort of deriving broader philosophical consequences. Well, here's another way that you could characterize theories from that perspective. You can characterize the theories in terms of the inferences that are immediately licensed. And so supposing I'm going to stop saying theoretical and operational spacetime. I'm just going to say spacetime sub A, spacetime sub B, and so on, right? These are all sort of different senses in which people use the word spacetime. And one thing you might think of doing is you might say, okay, so one way I can characterize special relativity is it's the theory in which spacetime sub A entails spacetime sub B. So any inferences that I have on the basis of saying it follows from the property of space, theory having spacetime sub A, I can also infer claims about that follow from something having spacetime sub B type properties, right? And that's the kind of thing that Eleanor does with spacetime functionalism in special relativity, and even to an extent in general relativity in the modulo the problem cases that James and I talk about in that paper.
So
where
okay,
basically,
yeah, oh interesting. So sorry, go on.
No. What were you?
Well, I just wanted to clarify. So the idea is that what Knox is showing is that one definition of space-time, namely the thing that gives you the structure of inertial frames, is going to be operational space-time. That is the thing that we detect with our measuring devices. Yeah. Okay. Great.
Exactly. And so what I want to say, so now coming to superspace, I want to say, look, here are different things. There's the theoretical, the what we've been talking about all this time, right? The Ehrman style, the Ehrman influenced common symmetry group type argument. That's going to give me theoretical space-time. What I wish I'd said in the paper now more clearly is Eleanor's inertial frame spacetime functionalism is its own thing, right? Let's call that spacetime inertial. And one way you can characterize special relativity and large chunks of general relativity is spacetime inertial entails operational spacetime. So what I'm trying to do, or one of the things that I was trying to suggest in the paper is another way to get at sort of an analog of spacetime inertial in the superspace case is to just, I used to jokingly say this, sort of all my papers are basically all the spacetime papers with the word super prefixed. But in this case, it's sort of, that's generally what it was. You can define these things called super inertial frames. So the obvious question to ask is, well, is there an analog of Eleanor's, of Knox style inertial frame functionalism? I mean, on the one hand, there's more than the analog. There is the exact identical thing, which is literally the same thing. Take the inertial frames of Minkowski spacetime, call that spacetime. I mean, this is stuff that you say in your paper. I don't know why I'm saying this back to you, but the
You're saying
so the other thing
that listeners.
The other thing. Oh God, there are listeners.
There will be, not yet, but there will be.
Yeah. Well, actually, there are. But God, sorry. Just luckily, you can edit out the silly indexical humor. There are now listeners. Anyway, sorry. What was I saying? Yes. So you can do the identical thing, right? And then what you'll get in superspace is the inertial frames, the Knoxian spacetime inertial. But you might also say, look, we've got this other structure. I mean, as with all of these things, right? You can, when you find a generalization of a particular structure, you can sort of naturally generalize that structure and say, do these things follow? Or you can just take the identical structure in these new models, and then sort of compare. And that's basically what's going on over here. I'm saying, look, since we've got more tools at our disposal, namely, we've got this thing called a supermetric, and so can we define something like a super inertial frame? The answer is yes. And then the question is that also going to be space-time? And the answer is sure, yeah. It'll be space-time sub super inertial. And then you can ask the question, is that the concept, is that the space-time concept that I should be using?
Yeah.
And what I want to say is, if you use that space-time concept, then the inference from space-time sub-inertial or space-time sub-superinertial to space-time sub-operational or operational space-time is broken in superspace. That's the I mean, in a sense, it feels kind of like I don't know. It feels a little bit like it feels a little obvious. If I were to be cynical, I would characterize it as sounding sort of quite obvious. But I think it's nonetheless, sometimes obvious. Sometimes it's quite useful to have obvious things.
I mean, I don't think it's trivial. So, for example, like you know, we could ask the analog of this for clearly internal symmetries, like
Yes.
like U1 gauge symmetry, and there wouldn't be an analog of the inertial frames, like I mean, so yeah, so it's like I don't think it's a trivial observation. I think it's an interesting observation and something that's kind of it's like this is one of the things that's interesting about supersymmetry is that um, it is a generalization of space-time symmetry in a way that other symmetries aren't. Right?
Yeah, I mean, it's sort of following in that kind of tradition of let's generalize or let's reformulate, and given a new reformulation, some things just become more salient. I mean, my favorite example of this is if you do general relativity using tensor calculus for years and years, and then Penrose comes along and does it all using two spinners, and then suddenly a whole bunch of things, the like the classification of spacetimes, Petrov classification just falls out sort of almost trivially in a way that sort of requires a whole lot of effort if you're
getting into
doing
stuff that I haven't studied, Tushar.
Well, I've spent a lot of time with Dennis Lemkool, who's been kind enough to sort of very, very slowly and patiently over many years say the same things to me time and again so that I finally understand them.
That does sound like this. Actually, this comes to something that I wanted to talk about with you in connection with your paper, and I don't think we have, which is this point. So there's a point that Tim Maudlin made to me when I was presenting about supersymmetry some years ago, which is, what Tim said was, well, look, why all this, to do about whether this is space-time that you're talking about, or like the supersymmetry analog of space-time. Minkowski didn't, when he came up with space-time in the first place, he didn't say this is the new notion of space, really. He said space and time by themselves are going to fall into the shadows or whatever, and we generalize and replace that notion with the notion of space-time, right? And so what Maudlin was saying is, well, look, why isn't that what we should say? That space-time has to go to the shadows now as well, and so does the notion of boson and fermion as separate types of entity. And assuming that supersymmetry is true, by the way, which I should say, by the way, is like an assumption we make for the sake of argument in this discussion. But of course,
this is why it's great to be a philosopher doing work on supersymmetry, whereas theoretical physicists, I feel for you.
Yeah, but we should be clear that this is not a theory that's been experimentally verified, and in fact has kind of like pointedly not been experimentally verified when many were hoping that it would be at the LHC. Still, though, it's entirely...
but luckily, I subscribe to a deontological view of justification, so I feel justified in believing that supersymmetry exists.
I, on the other hand, am a hard ass about justification, so I feel that I'm completely unjustified in believing it exists, but I am justified in talking about it. So that's all I want. So to get back to what Tim was saying, though, his idea is that these notions of space-time on the one hand and Bose-Fermi theories on the other hand, if we adopt a supersymmetry theory with a well-defined superspace background, the thing we should say is those concepts have fallen into the shadows now too, get rid of those, and instead we have a new generalization and just its own kind of new thing, which has replaced as a space-time as a better
Yeah.
entity to think in terms of.
So I don't know the extent to which I disagree with any of that. I mean,
Yeah.
this might turn out to just be a merely verbal dispute, because so I guess the way I want to think about it is, I mean, there's something not dissimilar. I mean, Kuhn says something not dissimilar, right? When he says, look, to to the Newtonian gravitational theorist and to the general relativist, the word space just means different things, and so it is conceptually incoherent
Yeah.
to say that space is curved to the Newtonian gravitational theorist, which I think is correct. But I think it's correct in a not super interesting way. What I think is more interesting from a sort of both a heuristic perspective in terms of sort of pushing forward our physics, as well as an interpretational perspective, right? Pushing forward our understanding of our best physics is, how can we, how much of what we have a good grasp on can we continue to hold on to, in the sense that how many of those the sorts of inferences that we used to make can we continue to make. I think Ollie Pooley says at the end of one of his papers, again I can't remember the title, I can't remember which one it is, but he says something like, you do more, not less, credit to hang on, I had it in my head just a second ago. Now it's sort of being hit by aphasia as always. Basically, okay, I'm not going to try to paraphrase, but the idea is, yeah, you do more credit to the sort of conceptual novelty of a theory by actually figuring out the ways in which it's similar to the theories that came before it.
Yeah.
Right? He puts it a lot. Sorry, Ollie, if you're watching this, he puts it a lot more eloquently than that.
Yeah.
But I think there's something similar going on over here, where sort of, really speaking, I think Tim Maudlin is completely right. Right? Superspace is not spatiotemporal in every way that Minkowski spacetime is spatiotemporal. In the same way that Lorentzian spacetime is not spatiotemporal in every way that Minkowski spacetime, Minkowski spacetime is a special case of a Lorentzian spacetime, right? But at the same time, I think, having pointed that out, I think that the bad thing to do would then just be to say, well, now I put up my hands and I'm not going to try to figure out I'm not going to try to figure out whether people who say things like superspace is spatiotemporal are saying something that's nonetheless going to give me good inferences, or not. I don't, at that point, to just put my hands up and go, oh, you supersymmetry theorist use the word spacetime to describe superspace, I have no idea what you're talking about, la 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 la. What I really want to be the case is to say, okay, you're using spacetime in this way. Here's how the 19 different versions, here's the inferential pattern that exists between these 19 different understandings of space, the word space-time in GR. Can you tell me about the set of inferential patterns that exist between your 14 uses of space-time in superspace and supersymmetry, and what kinds of inferences I'm allowed to make? And then you can say, oh, look, just as we made this claim about no signaling, for example, in special relativity, because this inferential link was maintained in SR, the analog of that inferential link is still maintained, surprisingly, in superspace, except that you have to generalize to talk about, I mean, I don't know if any of this is true, but except, you generalize to super Maxwell fields and blah, 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 blah. Can you make similar inferences? Maybe you can, maybe you can't. This is really a call for sort of clarity about basically that.
Yeah, good. Yeah, that seems right, and I think seems compatible with what Tim was saying. Yeah, like it's like when we moved from space to space time, part of what was interesting about that was the analogies that could be drawn between space time and space, and
yeah,
when I explain the idea of space-time to, like folks who aren't philosophers of physics or physicists, what I'll tend to say is something like, you should think of time as being like space, right? That's kind of where the insight comes in. And so similarly, the insight of this is you should think of actually the difference between bosons and fermions as being like space.
Yeah.
And that's kind of like spatial location in this in a sense. Like, bosons are located at different places in superspace than fermions are. Um, yeah, and uh, you know that analogy seems very useful in understanding what the field is
Yeah,
going to say.
look at how incredibly sort of conceptually useful fiber bundles are, right? I mean, it's the same thing. We're just sort of we're treating these internal spaces as spaces. In the sense, I mean, I think about fibers as sort of things that I can walk through in the same way that I sort of walk through space. You kind of you need that.
Yeah,
You don't want philosophers coming along and going, oh well, actually, I think you'll find.
yeah,
That's
yeah.
when dialogue stops.
Good, great. Okay, so let's talk about operational spacetime now.
Cool. Yeah.
And I realized as I was kind of preparing for this that this I've mentioned to you already that I realized as I was preparing for this that this is the part of your argument that I feel like I get less than the other parts. So I wonder if you want to kind of um, give the spiel about. So your argument is now one of the things I realized I was a little fuzzy about after reading the paper. I had always taken your view to be that superspace is not operational spacetime, but I wondered after rereading the paper, preparing for this, whether the view was, well, it's an open question whether it's operational spacetime or not, and the answer to the question that it's theoretical spacetime, yes, it is, doesn't answer the question of whether it's operational spacetime.
Yeah, I think that's right. And again, I hate to be one of those people who says, oh, I got that. I should have done it so much better when I had the chance. But there are a couple of things where I really think a few of the emphases could have changed. What's particularly frustrating is that the paper still isn't technically out, but I haven't been able to change anything in it for a couple of years.
That's edited volumes for you. I mean, journals also publish slowly, so
yeah. But I find it really funny that your paper that sort of discusses my paper came out a whole 2 years before my paper did.
But I don't think mine is. I don't think mine is actually out in an issue of Synthesa, though. I think it's.
Isn't it a Kentness?
Oh, mine is. Oh, right. Sorry, I was thinking of a different paper. It is in Kentness.
Oh yeah.
Maybe it is out actually.
I mean, I think it says 2019 online, but again, I don't know because I think Synthesa also puts
online access. Yeah. Sometimes they just do online access before they come out. Anyway, whatever. Like, who cares?
But yeah, so Anyway, to come back to what I was going to say, yes. So, I mean, to repeat slightly, but again, Fermi pleasure principle, right? Never underestimate how much pleasure an audience gets from hearing things they already know.
Jeremy Butterfield loves that principle. He would always talk about it.
I know. This is the dead giveaway that someone spent time with Jeremy. This and
right now you're at Cambridge, so you're like now you're living that principle. With Jeremy.
Absolutely.
Right, go on. Sorry.
So the basic idea is, look, you've got these different concepts, and I want to show how some of these inferences come apart, and I want to remain agnostic as to whether some of the other inferences remain. But when you ask a question of the form, does this structure remain in this new model? Effectively, the first thing you have to do is establish some kind of fiducial comparison structure to say, look, this is the analog of this thing in this structure, this is the analog of this thing in this structure, and now we can compare.
So what are the super rods and what are the super clocks?
This is So this is exactly the question, right? So here's basically my answer to how should we think about some of these the analogs of some of these inferences. I mean, I'm using special relativity as my starting point because all of this is discussed in the context of rigid, non-extended supersymmetry. So it's the generalization of special relativity, not general relativity. And basically what I want to say is, look, something like inertial frame functions spacetime to operational spacetime is one inference. Theoretical spacetime to operational spacetime is another inference. First of all, what's the analog of operational spacetime? Is it again just to be expressed in terms of rods and clocks, or is it to be expressed in terms of some kind of sort of generalization of rods and clocks, some kind of what I call super surveyors, right? If you think of rods and clocks as ordinary surveyors, you build out of these super fields some super surveyors, and of course lots of theory is going to go into that, right? Exactly like it's highly non-trivial, even if you have fields that have particular symmetries, that they're going to sort of coagulate in the correct ways as to give you sort of sufficiently robust things that can act as rods and clocks. All of the same considerations we worry about over here. And basically what I wanted to say was, whatever you choose as the analog of operational spacetime, and whatever you choose as the analog of the inertial frame spacetime, and whatever you choose, and sort of not whatever you choose as the analog of theoretical spacetime, because that's pretty straightforwardly linkable. Whatever you choose for all of these others, whereas you had these links in special relativity, there's reason to believe that you no longer have these links in superspace. And so exactly, so whereas in special relativity, you might have had something like inertial frame spacetime to operational spacetime. Over here, you'll have both super inertial frame to what you might call, I don't know, super operational spacetime. You might also have inertial frame to super operational. You might have super inertial to operational, all of the permutations. And what I want to suggest, I mean, I give a few reasons to believe that that some of those permutations might not work out, but I don't do it in a, I mean, this is again, this is to repeat what I said earlier about sort of wishing I could have done things slightly differently. I kind of wish I'd done it in this permutation way, and sort of given reasons to sort of be doubtful about all of these different permutations, which is what I am. I'm skeptical about all of these inferences following. But what I said in the paper was I just gave a couple of examples, and I just sort of left it at that. And I suspect that that's why it reads as not as sharp as maybe some of the earlier bits of that paper.
Yeah, I actually wasn't saying that at all. I was just saying that it was kind of, I think partly the controversy between you and me was about the question of theoretical spacetime. And so this is a part of the paper that I had kind of not devoted as much attention to in kind of previous readings. But like, it might help to get one of these examples on the table, actually. Do you want to kind of...
Sure. I mean, this is really basic and a bit crude. But you might think in order to survey some kind of geometrical structure, like a metric, how are you going to survey it? You're going to survey it via I keep saying rods and clocks, but I'll just say surveyors as the sort of generic term. You're going to survey it via some kind of physical system that evolves according to some dynamical evolution equations, right? And then you infer from particular dynamical behaviors some numbers, and those numbers will correspond to some magnitudes, right? You can't straightforwardly do that with a supersymmetric theory, because one of the things that gets kind of messed up is this sort of intuitive picture of a simple dynamical evolution along a single temporal dimension, right? So in ordinary classical mechanics, if I've got the Hamiltonian and I've got some temporal parameter, and obviously if I've got the appropriate symplectic structure, etc., then I'm fine, right? I'm off to the races. I know everything. There's no analog of a single parameter with respect to which I can give you some stuff, and then together with the theoretical structures of that state space, I can give you the dynamical evolution. Because one of the things that supersymmetric transformations do is they mess up the pure bosonic character of the temporal dimension, right? You get a bit of this sort of weird Grassmann nature when you super translate. You don't just change the positions. You don't just change the spatial positions to get this like weird anti-commutingness. You also get a bit of weird anti-commutingness in the temporal dimension. The second you have that, you've now completely lost this idea of a simple dynamical evolution along some trajectory in a state space. And that's really all the argument was. So now you no longer have this way of just operationalizing a measurement through dynamical evolution. And so the straightforward inference from I've got these symmetries and I've got this kind of theoretical structure to I can make certain operational claims about how surveyors, irrespective of what they're composed of, will behave.
Yeah. So just to be sure I'm clear, is the kind of like weird Grassmann valued character that comes into the temporal dimension, is this coming from the fact that, like, they say like a supersymmetry transformation or a super translation is the square root of a space-time translation, so that, like, if you apply the super translation once without squaring it, then you've kind of done something like the square root of a time translation, and then it's like
that's
what is that as as an analog of, like, time evolution or something.
That's basically it. I mean, the square root thing is a useful is sort of a useful way of keeping track mathematically, not of any. There's nothing, or at least I don't think it's right to think of the square root of that generator as corresponding to anything. But it's just a way of keeping track of the fact that that sort of repeated application of that generator is the thing that corresponds to something.
Yeah.
But I think having the square root in there is useful in the sense that it's not telling you that nothing happens between doing nothing and applying it twice. There's something that happens when you apply it once, but it's not. But it's something that sort of messes up.
It's not really a time translation. It's like,
but it's not really a time translation.
It's kind of, it's like part way to a time translation.
Yeah, that's right. I mean, the other, just a really quick thing, because I think this is a good time to mention this. So we talk about when you introduced superspace, and you introduced this idea of the generator of super translations squaring effectively to give you a space-time translation, and really that's where that's what's really suggestive of, that's where this idea of superspace really comes from. The interesting thing about that, though, is all of this is happening at the level of the algebra, right? So all of this is happening at the infinitesimal level.
Yeah.
And we're kind of used to dealing with, at least in the kinds of physics that we ordinarily do, dealing with with Lie groups, and in particular connected Lie groups, the components that are connected to the identity. And with respect to that component, you take any infinitesimal transformation, and you can always exponentiate it enough to give you a finite translation of sort of whatever magnitude you like. You can't do that with superspace anymore, and that's partially almost entirely as a result of this weird Grassmann character of the transformation. It stays spatiotemporal really only at the infinitesimal level. There's no way that I can go from sort of take a boson, super translate it to a fermion, then super translate it back to a boson, and then when I've done that, then I've got an infinitesimally displaced boson. Fair enough, but I can't keep doing that to generate a boson translation of a sort of arbitrary distance. It's always going to stop at the infinitesimal. At the infinitesimal level.
Yeah.
And that really the mathematical reason is we're not dealing with Lie groups anymore. So this connected component theorem just doesn't apply.
Yeah. This is good. I mean, this is one of the ways in which your paper on supersymmetry is kind of like a little richer than mine, because, like, I focus on the analogies between supersymmetry and other, stuff, and I think it's well,
that's very kind of you to say. I think the less generous way is to say this is why my paper is less focused than yours.
Good. No, this is really great. So, like, so conclusion then. I mean, this is, in a way, this is really great, because this is kind of like room for future work, right? There's this open question of whether at the end of the day there's a salvageable notion of operational space-time, operational superspace, for supersymmetry theories. So, I mean, this gets in a way to, like, a couple of the questions that I had to kind of wrap us up a bit. So one of the things, so you may, to this first one, you may just answer, like, I've already answered this, because it's come up a number of times, kind of like little pieces of an answer. But I was wondering if there's anything we haven't already talked about yet, that is like a way that you're thinking about this topic has evolved since your paper was kind of submitted in its final form.
Yeah, I mean, I think you're right. I've sort of dropped hints, basically throughout. But yeah, to sort of to put it all together, yes, I think I don't think there's anything that I have in that paper that I think is incorrect or that I disagree with. I think there are certain claims that I would hit a bit less hard, and certain other claims that I'd hit a bit harder, but with certain clarifications. But I think ultimately the way that my thinking on this has evolved actually is the result of the fact that after writing this paper, I spent a lot of time just writing papers on GR and spacetime. Did a bunch of work with people like James Reed and Niels Linnemann, from whom I learned a great deal. And I think I'm now sort of coming back to, I'm now working on supersymmetry again after a little while. And what I've sort of realized is the thing that both in this paper that we're discussing today, as well as in this other paper that I wrote with James that I made reference to, I think the thing that at least I was kind of gesturing towards without having sort of really been able to put my finger on it until now, is this idea that, as philosophers of physics, and especially metaphysically oriented philosophers of physics, it's sort of incumbent upon us to be clear about the sorts of inferences, metaphysical and semantic, that we're licensed to make. And I think also putting it that way maybe doesn't quite get at exactly what I want to say, because I also want it to be the case that I want to think of the inferences as being tethered to particular kinds of assumptions that we're allowed to make. I don't want to argue for those assumptions. I basically, the way I see things is a lot of arguments are of the form: here's claim A. It is obvious that claim A entails claim B. Therefore, claim B. That's the end of the story. And I think really what's going on is more like, here's claim A, which is plausible. The inference really is claim A conjunction with a whole bunch of things that I think you should take for granted and I think are obviously true, entail claim B. And what I'm interested in is taking stuff out of that bracket and sort of making it explicit in the long conjunct, in the antecedent of that conditional. And I see this paper as sort of my first attempt at doing that without realizing that that's what I was trying to do. But now that way of thinking about things is sort of shaping the way that I'm approaching all of this going forward. So just as a final quick thing about sort of, what I'm doing now with respect to all of this, Niels Martens, a good friend of ours, and I have been shouting at each other for years about metaphysics. And we figured the best way to sort out what's going on is to write a paper together. And we're kind of interested in one of the things that you mention at the end of your Susie paper, specifically Weingard on ontological unification, the metaphysics of ontological unification. And basically what the idea that I want to get across is, look, there's a claim that Weingard makes about circumstances under which you're allowed to make the inference from these are elements in a gauge multiplet to these are tokens of the same type. It's slightly different from what you propose in your paper. I still want to kind of resurrect what Weingard says, but central to Weingard's claim is a claim about spatiotemporal transformations. Right? He says, effectively says, spatiotemporal transformations are sufficient for being able to interpret things, symmetry-related entries in a gauge multiplet as being ontologically unified.
Yeah.
But now to bring it back to sort of the stuff we've been discussing all along, this is a totally different sense of spatiotemporal from theoretical or operational or superinertial or whatever. And what we're looking to do in this paper is try to spell out, the conditions under which you can actually make this inference, and then just sort of have that as a kind of, the broader project is to just sort of have off the shelf kind of inference boxes, and then just have philosophers come along and go, oh, I like, here's my antecedent commitment 1, antecedent commitment 2, antecedent commitment 3. Oh, here's the box on the shelf that's consistent with all of those. What am I allowed to infer from that? And so that's the way the project is shaping.
That's cool. No, I feel like the thing you set out to do in the Superspace paper has turned into a kind of programmatic project that's applying elsewhere. I really like that. Yeah. Okay, good. So So what Weingart says in that paper is that the distinction that matters is a distinction between internal spaces and external spaces, right?
Yeah.
So, I mean, your work with Niels is still in progress, it sounds like, but are you partial to the idea that that's the important distinction here, or do you
Yes,
think
yeah. So I think so. So again, it's a really interesting. It's not a big literature, right? Redhead wrote a little bit about this, and then Weingart picked up on this in a couple of papers, and then it kind of lay dormant until you and I started looking at this stuff.
Yeah.
I think I might be wrong about this. We're gonna get angry comments. We're gonna get lots of angry comments from philosophers of physics going, "Well, I'll have you know, in 1994 I wrote," but what's interesting about the Redhead Weingart stuff is Redhead talks about passive versus active transformations.
Yeah.
Weingart talks about physical space versus internal space, but also talks about abstract space versus physical space. And there's also and then in another paper, Weingart talks about spatiotemporal transformations and non-spatiotemporal transformations, right? And I think they're all they're pointing in similar directions, but they're importantly distinct. What I want to hold on to is this idea that it's this, or at least to the extent that I can, I want to hold on to the idea that it's really the spatiotemporality in a specific sense that's grounding this inference, and the way that I want to argue for that, or the way that Niels and I want to argue for that, is basically there's a hidden premise in Weingart's way of thinking about things, which is let's take the supersymmetry example for concreteness. He says, look, you can only talk about you can talk about fermions and bosons being ontologically unified if superspace can be interpreted spatiotemporally, right? But that relies on the idea that if we want there to be a unification, we need a superspace formalism, and that's, as you mentioned, that's not possible. We know that that's not possible for every supersymmetric theory. So now we've got a bit of a problem, because if you think that something like ontological unification should be modally robust in the appropriate sense, right? If two things are ontologically unified in one normically possible world, they should be ontologically unified in all normically possible worlds. And you might deny that, but I think that's a reasonable thing to assume. Then we've got a problem for ontological unification of bosons and fermions, under the assumption that the only way you can do it is by going into the reduced formalism, which is the superspace formalism. But there's another way that you can think about how to interpret symmetries, and this is Neil Dewar's sophistication, where you say, no, I can still think of something as being a space-time symmetry, even if it's not a symmetry of a reduced spatiotemporal structure. And so again, this is another example of two different senses in which people might use the word space-time. I might think of space-time symmetry as being as piggybacking on an antecedent understanding of some spatiotemporal structure, right? I start off with a spatiotemporal structure, and then that spatiotemporal structure will have some symmetries, and in virtue of being symmetries of that structure, these symmetries are spatiotemporal. But I might go the other way around. I might start off with the transformations themselves and say, look, some forms of symmetry algebra will be symmetry algebras of spacetimes, and others will not be. And then the structures that are invariant under those are the things that I'll talk about as being spatiotemporal. And if you're a reductionist, if you think the only way you can do this is by talking about superspace, then you're a bit sunk. You can only go in the direction of structure to symmetry group. Yeah. But if you're a sophisticate, you can go in the other direction. You can say, no, I have other criteria. For example, it's the common external dynamical symmetry group. And that characterizes the symmetry algebra directly. And then you say, okay, well, now I've got something spatiotemporal. If I now accept a sophisticate's view of spatiotemporal of interpretations of symmetries, then I can get the ontological unification thing off the ground by embracing the Weingart thesis, understanding space-time not in the theoretical or operational or blah, blah, blah sense, but in this new sense of well, maybe not the new sense, but in this distinct sense, which we can just call space-time sub Weingart.
Yeah,
Sorry, that
cool.
ended up being a bit more in depth than I intended. But
I mean, I think its depth was a virtue. I think that was super interesting. Like, yeah, I'm still trying to figure out what I think about uh, sophisticationism. I mean, it's obviously it's a view that's been in the philosophy of physics for a long time in some form. It comes from
yeah,
like sophisticated substantivalism. But I think one of the things actually that Neil Dewar's work has revealed is that like people who called themselves sophisticated substantivalists all along were actually thinking a couple of different things by that, and they didn't realize it until. I mean, so to me, I feel like an antecedent to this is Shamik Dasgupta's essay, "The Bare Necessities," where Dasgupta says,
yeah,
"Look, you can't just say that like two putatively different possibilities are actually no different in reality. You have to explain why they're no different in reality. You know, like uh, which is very close to the view that you were just calling reductionism, right?
yeah,
Um, whereas, and to me, when I kind of encountered that view when Shamik was developing it, I had a couple different reactions, but eventually my reaction was, I guess that was what I always thought sophisticated substantivalism was that sophisticated substantivalism
hmm
was this promissory note that eventually there would be a view um, that didn't mention the stuff that wasn't invariant under symmetries at all. And uh, clearly others didn't think of it that way and were thinking of it like, no, you know, there's nothing wrong with talking about stuff that isn't real as long as we point out that we're saying it isn't real, right?
yeah,
Um, yeah, so this is, I mean, I think of this as kind of like one of the most uh, deep and lively disagreements about the nature of symmetry that exist in the field right now.
yeah. I agree. That's why we're jumping on the bandwagon.
Yeah, yeah. So is is do I infer from this that you and Niels Martens are now kind of like sophisticationists in the like? Are you
Oh
committed
no.
to
Well,
Dewar's view?
I am. I very much am.
Yeah,
Niels is not,
yeah, yeah.
and and again, sort of
Right, because Niels has a paper criticizing
yeah,
Dewar
yeah,
with
exactly.
James Reed.
With
Yeah,
James, yeah,
yeah.
yeah. No, Niels is not on board with that view. I'm hoping that in writing this paper he'll come around to that view. But also, I think the goal in this paper is not to argue for sophistication. It's to sort of lay out what other things you have to accept in order for the sophisticate's view
Yeah.
to be available to you, and lay out the things that need to be around in order for some alternative view to be available to you, and then just say, look, you know push comes to shove, I think this package is the one that I want, but look, here's another package that might be available to you. And I think this is the great advantage of writing a paper. This is the first time I'll be writing a paper with someone with whom I don't agree
Yeah,
about everything. So
yeah. Good stuff.
it's yeah, famous last words maybe, but it's a great deal of fun at this point.
Yeah, excellent. All right, this is great stuff. Tushar, I enjoyed this conversation very much, and I hope that
Oh, Dave, this was fantastic. Thank you
yeah,
so much. I had such a blast. This is great. I mean, I wasn't lying. At some point, I did forget that there would be other people.
yeah, yeah.
It's lovely just to catch up and
I know, yeah,
and
it's
have the
great
time to
to.
talk about this
We'll
stuff.
have to catch up about other things too. But yeah, I hope this will be a good companion to your paper that folks can consult and either
Yeah,
use
no,
as a way of getting into it or as a way of getting more out of it.
yeah, no, I hope so too. I mean, I wish everyone. I mean, it'd be lovely if everyone had the option to sort of revisit the 3, 4, 5-year-old papers and sort of because you're never in a position where you say, oh well, I wish I could just sort of add a little bit more and have that published as an addendum.
Yeah.
So this is I
This
guess
is
the
the
next best
addendum.
thing.
Yeah.
This
All
is the
right.
addendum indeed.
All right, wonderful. Well, uh, thank you for being on Author Meets Physics. I'm excited to get this out there.
Yeah, thanks so much for having me, Dave. This was absolutely fabulous.